All right. So in this lesson, we're going to start looking at air resistance and see what does air resistance actually do mathematically if we do start to account for air resistance. It's worth pointing out in many situations that we deal with, air resistance is indeed negligible. And we can actually describe why that is as we kind of get through this type of lesson and actually kind of think about the situations where it would not be negligible. But we're looking at what would happen if it's not. What happens if air resistance is a significant force acting on an object? So say I have a ball and I drop it out of an airplane flying at, 30,000 feet. We know we have the force of gravity acting on the ball, but at some point we're going to have another force acting on the ball, what I'm going to label as FD. This is the force of air drag or the force of air resistance, and that's going to be upward. So for the purposes of this lesson, when we look at FD, we're going to think of this situation as being our primary situation. The interesting thing about FD, for most objects, the force of the air resistance is related to some constant times the speed of the object squared. So the faster an object moves, this air resistance force increases by a factor of v squared. So if you double the speed, you quadruple the force of air resistance. Now you might ask yourself, what are some things that are in this constant K? We'll talk about that here in a second. So this constant depends upon really a few different things. One is what we call the cross-sectional area, or the effective cross-sectional area. What that means is if you were looking at the object as it's moving, what is the area that you see? So for example, for this ball, it would really be if you cut the ball in half, what's the area of that half? That's kind of the effective cross-sectional area. The second one is what we call the drag coefficient. So A in my equation down here is the drag coefficient, or A is the cross-sectional area, C is the drag coefficient. That basically is determined by how does that object interact with the fluid or the gas that you're going through. The one thing to point out with fluids or gases is that gas is really like a fluid. It really behaves the same way in this case. So this would also work for fluid density. So you're looking at something sinking in the water. And then density of your fluid, which I use rho to signify density. So really this constant can be written as 1/2 C rho A. So you really need to know three things: the effective cross-sectional area, the drag coefficient, which is dependent on what is the object and what is the fluid that it's going through. Is there some attractive force between those we don't know about? And then how dense is the fluid? Density would play a role because if there's more particles to interact with, this force should get bigger. So really we could write this as 1/2 C rho A V squared. So the reason why we don't deal with air resistance, first of all, in many cases, is that there's lots of other things we need to know in order to actually do that. So the next thing we want to do is we want to calculate terminal velocity. And terminal velocity is really actually kind of a cool thing when we talk about air resistance. What terminal velocity is if I drop this ball out of the airplane, what is the maximum speed the ball is going to reach? So we know that we have this force of weight pulling me down, and I have this drag force that's pulling me up. Initially, the drag force is 0 because you start at a velocity of 0, but your weight is a fixed number. But your velocity starts to increase, which means your drag force starts to increase. And so at some point, the drag force and the weight are going to be the same. We're going to be in equilibrium, and we'll move at a constant velocity. So the way to figure out what the terminal velocity would be is to take drag force minus weight and set it equal to 0, and then solve for v. And so if I plug in what the drag force looks like, we can do a couple quick steps of algebra. And what you find out is that the terminal velocity is really related to the weight of the object. Heavier objects have higher terminal velocities. So if you had a tennis ball and then a tennis ball that you cut open and filled with lead and sealed up, they're going to have the same cross-sectional area and the same drag coefficient. You'll drop them through the same fluid, but the weight of one is bigger than the weight of the other. So one would actually have a greater terminal velocity than the other one. This would be why if you do something like drop 2 balls off the clock tower, one ball may actually hit the ground first because of the fact that it has a higher mass. So let's do a quick problem dealing with air resistance. And let's say we have a raindrop with a radius of 1.5 millimeters and it falls from a cloud of a height of 1,500 meters. This is not all that unreasonable. Most of the clouds that you would have rain coming out of, that would probably be about the elevation most clouds are. We've done the drag coefficient in the air and found that it's 0.6 for a raindrop. And we're going to make the assumption the raindrop is spherical mostly throughout its fall. The density of water is 1,000 kilograms per meter cubed, and the density of air is about 1.2 kilograms per meter cubed. So the density of air is actually pretty small. So I want to know how fast is the raindrop moving if we include the effect of air resistance. So first of all, if we did no air resistance, how fast is the raindrop moving? Well, 1/2 mv squared equals mgh. You can cancel the m out. V squared, or half v squared equals gh. V squared equals 2gh, so v equals the square root of 2gh, and you end up with 171.5 meters per second. Well, I can tell you something. If you were getting hit by raindrops moving at 171.5 meters per second, you would be in some trouble. This raindrop, if we actually work out its mass, what would that end up being? Maybe a gram or so of mass. 100 meters per second, or almost 200 meters per second, that's like the speed of like a large caliber handgun bullet, like that type of speed. So you'd be talking about something that would actually do some damage if it hit you. But let's look at air resistance. What we can say probably about the 1,500 meters is that's a far enough distance that it's fallen that we've probably reached terminal velocity at this point. We could actually work that out and see if that's true. I'm going to tell you in this case it's probably true. So first thing we want to do is figure out the mass of the raindrop itself, and here I do density of the water, 4/3 pi r cubed. The cross-sectional area is really pi r squared, because the raindrop is a sphere. And so if I substitute those in there, I end up with an equation that looks like this, which is a kind of a big mess. So you can already start to see maybe why there's some reasons why we don't include air resistance. The one thing to point out is that the height we've decided doesn't matter because we've reached terminal velocity. If I take and simplify some things down, some r's and pi's cancel. And so I end up with that. And what you end up with is that the terminal velocity of the raindrop is 7.4 meters per second. That's not that fast. I could probably run faster than 7.4 meters per second. So that seems a lot more reasonable. The second problem I have for you comes right off of an AP exam, and this came off of the exam in 2000, and this came off the mechanics section. And so I'm going to read this exam word for word and work through every part. I've added in additional questions so we can kind of have some discussion about it. We're going to have a rubber ball of mass m dropped off a cliff, and as the ball falls, it's subject to air drag, a resistive force caused by the air, and the drag force on the ball has a magnitude of bv squared, where b is a constant drag coefficient and v is the instantaneous velocity. It says b is proportional to the cross-sectional area of the ball and the density, but does not depend upon the mass of the ball itself. And so really what it's saying about b is that the b they're defining here and the k I defined earlier are really the same value as what they're telling you. And as the ball falls, it approaches a constant value called the terminal speed. Well, that's what we really just talked about. So in the figure below, it wants us to label the forces at some instant before it reaches the terminal speed. And we have mg and bv squared up. That's what you would need to do in this. Label the two forces. Weight going down, bv squared going up. I'd have to go look at the scoring guide, but I'm willing to bet this is probably 2 points. One for mg going down, one for bv squared going up. The next one says, state whether the acceleration of the ball of mass m increases, decreases, or remains the same as the ball approaches terminal speed, and explain your answer. Well, the acceleration of the ball will decrease. The reason for this is as the ball falls, its velocity is going to increase, which means the drag force on the ball increases. As the drag force on the ball then increases, the net force on the ball, which would be mg minus bv squared, gets smaller. And it would get smaller until it gets to 0. When you get to 0, you experience no acceleration and you're at that constant velocity, that terminal velocity. Now here's a cool one here. It says, write but do not solve a differential equation for the instantaneous speed of the ball in terms of time t given the quantities and fundamental constants. You'll sometimes see them do this statement. When they're talking about write but do not solve a differential equation, what they mean is they want you to write a function or an equation that contains some function and possibly derivatives of that function. So in this case, v and a would be good examples, where a is the first derivative of v. So let's look at what they probably want us to do in this one. Probably what they do is say sum of forces equals mass times acceleration, or net force does. Well, I know the net force is weight minus bv squared. So if I wanted to solve this out, I know acceleration, another way to write acceleration is the derivative of velocity with respect to time. And then if I divide both sides by m, I actually get my differential equation here. The dv over dt is equal to g minus b over m v squared. Essentially what a differential equation is, it's a fancy way of saying you have an equation that contains a function that varies and its derivative in the same equation. In this case, v is a function that varies and dv over dt is the derivative of v. Now they tell us not to solve that for a number of reasons. One of it would be we probably need to know more advanced mathematical techniques to actually solve this one out. This would be one that's not particularly easy to work out. They would also not assume that you know integration well enough to actually plug through and solve that out in this particular instance. Now, if you take a class in differential equations at some point, you may actually encounter this type of problem and come up with what are the general solutions to this type of problem. One thing you find in differential equations is that there's certain differential equations that show up over and over and over again, what I call the common ones, and those are ones that have set, defined, known solutions. And so if I knew what dv or dx over dt equals some constant minus a constant times x squared, if I knew the general solution to that differential equation, I could maybe figure out what the function of v actually looks like. Now, determine the terminal speed. Well, the way to determine the terminal speed is that's the point where the weight and the drag force are equal to one another, or acceleration reaches 0, or dv over dt equals 0. So we can actually solve this out by plugging that in there. If you do some math, it looks like you'd subtract, or I added b over v vt squared. Divide all that across, basically multiply by the inverse fraction, and then square root everything. So the terminal velocity is really just the square root of m over b times g, and that'd be your terminal velocity. You could actually look at the units here and prove to yourself the units work out, and they actually do. So what I did next was I decided to graph a velocity of the function of time following. It says note that this is not asked during this AP exam or on this AP exam question, but I actually think it would be a fair question to ask you. What's true when it first starts to fall is the velocity is small enough that the acceleration is pretty close to m, is pretty close to g. And so at the beginning you should end up with something that almost looks linear, where g is the slope. And so if we look at the beginning, the first little bit of this almost looks linear. If we actually were to work that out, we get g. Well, what starts to happen is as v gets bigger, that acceleration should get smaller, and it should get smaller by a factor of v squared. And so what starts to end up happening is it starts to level off, level off, level off, level off. So acceleration gets smaller and smaller, closer and closer and closer to 0, until we get to here, where the acceleration is 0. And I actually know what the value of that speed was. So they kind of asked what to graph velocity as a function of time in this case. Probably what they're going to look for are a few things. One is that you have an asymptote and that you've labeled the asymptote with the terminal velocity. One is that you started off with a slope that was nearly linear and it kind of curved toward that asymptote. They probably won't be very picky about how it curves as long as it's not like a straight line and then levels off. In this particular instance, there are some instances where you can get differential equations which look like exponential, and you know that it's got to be exponential, and then they would expect something that looks like e to the x. We'll talk about that when we get to those types of situations later. Now, the last part of this question that was actually a part of this question was to determine the energy dissipated by the drag force during the fall if the ball was released at a height h and its terminal velocity was reached before hitting the ground, in terms of the given quantities and expressions. The way that I would do this is to figure out, well, the work done by the ball, that's going to be equal to the initial energy minus the final energy. And the reason why I did initial minus final in this case, rather than final minus initial, is I know that the work being done by the drag force should be negative. So really I've kind of flipped it around. It's actually talking about determine the energy dissipated. It's really kind of talking about an exponential value, or an absolute value. So I plug some things in here. Initial potential energy is all I have, mgh, and then when the ball hits the ground, is no potential energy, as all kinetic energy, 1/2 mvt squared. And so if I plug in what vt looks like, there we go. We can actually then pull some things out, and we end up with is that energy dissipated looks like mg times h minus m over 2b. And so this would be the energy dissipated by the drag force during the fall. The work done by the drag force would be the same value, only a negative number. So that's kind of a quick overview of the drag force and air resistance and how that actually plays a role. Some reasons why we don't begin to account for it. One is, in lots of situations it is actually negligible or close to negligible. The reason is, if you're moving at small velocities with fairly large objects with fairly small cross-sectional areas, you end up with something that usually ends up being pretty small. That's true for lots of situations that we deal with in physics. The main reason, or the main point of that, is small velocities. There's lots of situations we deal with that are small velocities. It also is mathematically difficult to deal with, so that'd be another reason to mostly ignore or not account for air resistance.